Alright, well, that will have to do. Okay, well, hello everyone. So, I'm Funai from MIT. And what I'm going to talk about is covariant band limitation in chemical theories and its effects on technology. So, this is the slide I always put up at the front of my talks. It's basically a description of my main interest, which is how detectors or atoms interact with particular fields. And what we will find actually as a result of this particular research project is that this description is slightly too simplistic because we sort of assuming that this is a simple task to create a particular field configuration. So what we should really be focusing on is specifically how the field created by one detector field, so the response of the second detector. So that's basically the basis of entanglement harvesting at its core. Okay, now, what is a UV cutoff? So, a UV cutoff is something which restricts the existence of particles at certain momentum. So, for example, one which we are more likely familiar with is if we have a field operator phi, then it's usually standard free space notation is integral 3k and all this rubbish, and we put in this Heaviside step function. This Heaviside step function tells us that we are forbidding the existence of excitations above an energy of lambda. Okay. Now, these sorts of things either appear in QFTs, we want to do numerical renormalizations, or they appear more physically in condensed matter systems, for example, which have minimum lengths associated with them. And our focus really comes from the fact that if we have systems of generalized uncertainty principles, we expect them to also have minimum lengths, so we expect a UV cutoff to appear. But unlike condensed matter systems, we need a covariant cutoff because we're using covariant theories. So what does a covariant cutoff actually mean? Well, there is no foolproof way of defining it, but one of the ways we've chosen to define it is to say, for instance, in fact space-time, that the 4-vector the contraction of the 4-vector Kmu, its absolute value will be less than lambda squared. And basically that's because Kmu is the only 4-vector associated with the only 4-vector which we can genuinely say is covariant in the QFT. Okay. So we note that when we have a non-interacting theory, sort of similar to what this is at the top, then this cutoff will do nothing because already the K0 term is already on shell with the spatial components of the K4 vector. However, if we consider something like the Feynman propagator, we find the covariant cutoffs will affect the Feynman propagator, and of course Feynman propagators appear in interacting theories. So if we have a Feynman propagator which in its covariant form is written as a 4 integral over e to the I k mu x minus x prime divided by k mu k mu, the covariant cutoff will introduce a Heaviside step function which truncates this integral, and that will have an effect. Okay. So that's basically a broad picture of how UV cutoffs work. Now, to give you some sort of diagrammatic context as to what this means, is on the right-hand side we have, for example, spontaneous emission of a photon by a detector. So we have a detector in its ground state, and then at some point it spontaneously excites while emitting an excitation. Now, this excitation will be, for example, a photon. It will be on shell. That means that when you write out the 4-vector Kmu, it will be omega minus k, where it follows the on-shell condition. Which means that if we apply a covariant cutoff to this system, nothing will happen. But if we apply a non-covariant cutoff, it will happen because we won't allow photons with an energy larger than lambda to exist. But if we consider on the left-hand side something more similar to what we find in entanglement harvesting protocol, where we have two detectors in their ground states and then they become excited by some form of communication. This squiggly line here is a virtual particle, not an on-shell photon, which means that when we apply our cutoff, we actually have some changes taking place. But a non-covariant cutoff will have the covariant cutoff won't have an effect on the right-hand side, but it will on the left-hand side. And so those are some of the subtleties which will appear in this problem. And it will all boil down to whenever you see a Feynman propagator, you just start cutting away at it. Okay. Mathematical implementations. Okay. So, how the covariant cutoff actually comes about is best seen in the path interval quantization picture, and that's where most of these rules were derived, but then they follow on quite naturally into the canonical picture as well. So it boils down to sort of 2-point functions in the path interval picture, which of course are Feynman propagators, and so the covariant cutoff actually just restricts the integration domain in the path interval quantization picture. And again, that boils down to introducing this Heaviside step function. It's important to note that advanced and retarded propagators will also be modified in the same way, and that's mainly because these propagators differ from the Feynman propagator purely by a non-shelf property, which is unaffected by the cutoff. Now, in canonical quantization picture, the way we would interpret this sort of idea from particle quantization is that whenever we perform Wick contractions, instead of if we have a covariant UV cutoff, this Wick contraction term here, phi x, phi y, which would normally be a Feynman propagator, we'll just replace it with our UV cutoff Feynman propagator. And if you want to see an alternative picture of how we would go about performing this cutoff, we just look at the exact definition of the one of the forms of the Feynman propagator. At least this is actually one of the retarded or advanced propagators. But the introduction of a step function, which is the time ordering operation, which is inherent in the propagators, that has to be considered when you're taking the UV cutoff. So let's just ignore the projection, the phi detector for now. But we expand the Heaviside subfunction into its Fourier components, and then also the 2-point function, the expectation value. And we find that between this e to the I nu t minus t prime and this e to the I minus I omega t minus t prime, those have to be considered when you're taking the covariant UV cutoff. So that's why we now have a Heaviside step function which includes omega minus nu as well as the special component k. So that basically is the same thing as this equation 3 at the top.
Nick, a quick question, if it's not quick then. I always used to think that we don't do this in Lorentz signature simply because once we get to something to time-like vector which is very close to null, this is not really a restriction on anything. And that's why covariant of this form is efficient only in the Euclidean in Euclidean calculations. But probably I'm missing something.
So you don't do it?
I thought that wasn't a very useful option of introducing cutoff in Lorentz signature, simply because you can have arbitrarily large values of energy for vectors which are very close to null.
I guess it depends what your objective is.
Oh, probably.
So you're right. It doesn't limit the energy a particle can have. But basically what it's doing in a sense is minimizing the channel capacities of this particular operation.
Okay, so basically you don't care with its use in normal renormalisation. For the purposes of what you're interested in, it's enough.
Yeah, well, see, this is one. Another one can you is R4. Okay, is that the Euclidean? No. Well. That would be a Minkowski 4-dimensional space. I guess the KU would belong to a 4-dimensional, 3 plus 1 dimensional Minkowski space.
R4 doesn't specify the signature.
Yeah, perhaps I should put 3 plus 1 instead.
The big issue is that once you move to a Lorentzian cutoff as opposed to Euclidean one, you can no longer use it as a renormalization.
Yeah, but basically, okay. So, but since your goals would be different, that's okay.
So to be fair, so you say it can't be used. I haven't checked it. Can't be used for renormalization.
Not in the usual way.
Not in the usual way. Fair enough. Basically, what we do now. So what Martin Kempf and Pye showed us that generalized certainty principles imply, or we can derive this covariant cutoff from generalized certainty principles, which means that we're just looking at the effects of such a cutoff. on and see if it can be physically measured in a sense. Alright, so the model we'll be using is a standard 100-bit model. So we have a bias bandlimit field, and we just have two-level systems, two-level detectors, sigma xa and sigma x a and b. And it's just a linear coupling strength. I is a switching function, so that tells us when the detector is on and off. Sigma is the monopole moment, and f is the series, so it tells us the detector size. Well, whereabouts you'll be able to find and where it is influenced by the field. And just for numerical reasons, we just used Gaussians for both the switching and the smearing. Strictly speaking, that means that at some point the detectors will overlap, but for numerical purposes, the overlap is normal to be ignored. It also provides significant numerical advantages or analytical advantages. Okay, so for those familiar with harvesting, this should be more or less familiar. For those who aren't, I'll just point out some key features. So we start initially with both detectors in the ground state and the field in the vacuum state, and following interaction we trace out the fields, and this is what the two-detector reduced density matrix looks like. So it basically consists of a series of Whiteman functions on the top three lines, and then on the bottom two lines you can sort of see how we have a heavy-side step function, which means that these are no longer Whiteman functions, but there were combinations of Feynman propagators and advanced and retarded propagators. So that means that when we implement a UV cutoff, a covariant UV cutoff, these two lines are the ones which will be affected. And so it's often also putting the first form with this particular custom matrix for those who are familiar with that. Comfortable with that? Alright. So this is let me take a step back. From this density matrix, what we're going to do is we're going to compute the entanglement negativity between the two detectors. That involves taking a partial trace and then looking for any negative eigenvalues which result. That will be the measure we use to determine how much entanglement there is in the system. And if the negativity is 0, then if we're working with 2 qubits, we know that there will be no entanglement at all. So just to clarify that. So that's what we calculated here, more or less, is we've plotted out where the entanglement negativity is 0 and where it isn't. So if we look at this top left-hand side of the diagram, that tells us that the entanglement negativity is non-zero. So that means no matter how small it is, you can, in theory, extract some sort of usable entanglement. On the bottom right, you can't. And these two lines, the dotted line indicates the boundary between harvesting possible and harvesting impossible when there is no cutoff. And the solid line is when there is. So you can see it sort of oscillates back and forth. And if we actually just zoom in on this red box area here, which is what we've plotted on the right, you can see a little more clearly, you can see the behavior again. It starts separating, and it just increases the range of entanglement. And this effect here is actually it's not a harvesting effect, but that just is a result of the fact that when the two detectors overlap significantly, then the major source of entanglement isn't harvesting itself; it's really just inter-detector communication, and the cutoff reduces the channel capacity there as well. So this oscillatory behavior is kind of nice because it sort of reminds us of what we see when we do a covariant cutoff. So similar sort of oscillatory behavior appears. And if we sort of just have a look at how the entanglement range increases as a function of energy gap of the detectors, we see this highly oscillatory behavior. So the solid line is once again when the cutoff is 0.1 divided by sigma t, so that's just to get to any-dimensionalize it. And the dotted line is more or less approximately twice the cutoff. And you see the characteristic that the amplitude of this oscillation halves, or more or less halves, and it's twice as frequent. So basically, you can see that this will suggest a trend that will appear, which is that as the cutoff increases, these oscillations will be damped and become more frequent until basically they're non-existent.
And very high frequency.
Very high frequency, yeah. Now, I'll just show you these graphs again. So now what I want to look at is taking a slice along this axis, along this line, and showing the quantitative results of the entanglement harvesting. So instead of just showing black and 0 and 1, I'm going to show you how much entanglement activity is along this line, as well as along this line. So for large energy gap and for small energy gap.
Oh, this is the massive field here?
It's a massless field. Okay. So for large energy gap, we make approximately 40 times the inverse of the solution function. More or less, the behavior is unchanged. It's very subtle, the differences between them. The major differences actually appear when R, so the detector separations, is so small that again you have overlap. So that's where you see a major difference taking place. And then when you get to the point where you start seeing when harvesting becomes possible, that's where you see the basically between here, that what that's telling us is that the main contributions to entanglement harvesting lie within the threshold of the covariant. There's not much change. If you want to measure a difference, you have to look at the boundary of entanglement harvesting range.
The cutoffs are smaller than the frequency
Yep. So 0.01, 0.1, 0.2, 0.3. And the last one is 10. That's so behaves more or less as a no cutoff.
So once your cutoff is smaller than the characteristic frequency of switching, then you just don't see it. I'm sorry. Once your cutoff is bigger than the frequency. In other words,
yeah, I suppose you need to find a diagram to see any differences, but it'd be much less, or I think more challenging to see. This is basically the same diagram, but for small omega, for small energy gaps, and the reason it looks so different is actually because if we compare R, it goes up to 80, whereas in the second diagram it only goes up to 2, or 3. So basically this is a consequence once this actually is more or less a description of what happens when the two things are overlapping rather than the effects of harvesting. Which suggests really that harvesting might not be the best place to see these effects, but rather in just communication protocols. So that's sort of the little side project I did at the as well is does the covariant cutoff allow for superluminal signaling? So we said that it doesn't the covariant cutoff doesn't affect free photons traveling through space, but communication between two detectors would include communication from virtual photons as well. So basically, we have the same equations running, but instead of doing the harvesting protocol, which is having the two detectors more or less simultaneous according to some observer, I'm going to put one more or less, or very close to being in the causal path of the other, and then seeing if we can get superluminal communication from there. And the way we do that basically is by saying that if Alice is the one to interact first, we trace out Alice's contribution to Bob's density matrix, and if there is any dependence on lambda A, then there's communication. So if we do that, then all these expressions up here, they're just the various contributions from Alice and Bob and so forth. But what the important details can be shown here. So depending on the initial conditions of Alice and Bob, you get some sort of magnitude contributions to the transition probabilities, but they all depend on these delta functions. So the detector separation minus the time between them. So this is basically a rewriting of Huygens Huygens principle by saying that two detectors cite each other if they lie on each other's light cones. And this additional contribution here for this SCRI term is an effect of the covariant UV cutoff, which we write here. So if we take capital lambda to go to infinity, basically these two integrals vanish. And so knowing what this looks like will tell us a bit about how how either causality or non-locality is introduced as a result of this cutoff. And this is what it looks like. For t is equal to 0, so I depend on t, so I just let set t to 0 and just have a look at how it looks and sort of get the oscillatory behavior. And it doesn't decay, so this oscillation is very similar to the sort of intuitively, it's very similar to the oscillations you see in the non-covariant UV cutoff taking place. So basically, you can see that one of the reasons why the harvesting protocol had an extended range was because we were getting superluminal communication between the two detectors in question. And that's something which has to be considered. Right. Importantly, I haven't really shown it why, but if we look at the field expectation values after the first detector interacts, the energy is altered. But the information, basically, this is telling us that the information moves superluminal. So we have a disparity between the location of the energy and the location of the information. That tells us that one of basically it's telling us that how we define the location of the energy needs to be changed. There's a slight flaw in trying to define exact positions from field expectation values when you have a covariant cutoff. We should be using pure VMs or PVMs. So basically that brings me to my conclusions that so covariant UV cutoffs only affect interactive theories because they only affect basically final propagators in offshore quantities. As a result, covariant band limits seem to improve the range of internal harvesting. We just said this is the superluminal behavior which introduces. Detector self-interaction is similar unaffected. So if you only have one detector interacting with a field, let's say excitation probability, at least a second order calculation field, suspect high. It doesn't seem to be affected by the introduction of these cutoffs. So you need two detectors to see its effect. And as I said here, so we have a little superluminal signaling introduced by this. Now that oscillatory curve I showed you before, the graph, suggests that there may be a possibility that we could get a covariant sampling theory from it, but that's a very weak idea at the moment. It's very hopeful, but there's no guarantees there. Now, future work, I'll try to derive generalized consequences from this, and also try and resolve the issue of superluminal behavior concerning static energy locations. Anyway, that's all I've got.
Questions from them?
Because I'm sure this issue with the cutoff not affecting the single detector interactions, is that just because the final propagator doesn't turn off the single detector interactions?
It doesn't.
Lower order federation?
Yeah, it doesn't show up for lower order federation.
Yeah, so the model you had for the time-dependent coupling of the detector to the field, it was a Gaussian?
Yes.
So that has like infinite extents.
Right,
Past
yeah.
the future.
So
If you try something that has like
for the harvesting, that's
zero
true.
and zero times.
For the harvesting, that's true. But this result, it actually has general Chi's and F's, so this is independent of that.
Okay.
Yeah.
So you consider it where you'd actually like literally have to be coupling to zero and stuff.
Yeah. So if I were to do that for the communication protocols I have, Jen would definitely see it again. Explicitly. Basically, this kernel of the interval is introducing superluminal behavior for any series and any switches. Okay? Cool. Any questions? Right. Great.
Okay. Thank you. Same computer?
Yep.